उसका मैसेज।
बहुत सही बंदा है ना, ये जो चीज़ हैंडल कर देता ना, आप बोला किसी को पैसा कमा दूंगा
देखता कोई नहीं है सीधे लाइव में।
टाइम कंप्लीट हो रहा है ना, 4 घंटा हो जाना है।
मोनेटाइज करने के लिए लगल है। तमाम 1-2 करोड़ हमरो देना।
कमाएंगे
चलिए बढ़ते जाइए सर, बढ़ते जाइए। यहाँ से तो आगे चढ़ेगा, नहीं तो जरूर। मेरे टाइम में 10% यही होता है और बॉयज का सिर्फ वही बोलते हैं। ऐसे मतलब चालू भी होता है। तो पास ही है। यहाँ फॉरेन रेस्टोरेंट आपके सेल प्रोग्राम है।
चला जाए आगे। वो कहाँ गया?
इसमें कहाँ गए? इसमें गुड मॉर्निंग सर। हम इधर बैठते हैं, सर के साथ डिस्कशन करना होगा इसको। यहाँ से बंद चाहिए एसी का, यहाँ से ऑफ।
Good morning, sir. Recite this. The finished teacher.
बाहर से आराम से
I'm listening.
Okay.
Sorry for the delay. Good morning, everyone. It is my privilege to introduce Dr. Akhilesh Prasad, professor in the Department of Mathematics and Computing at IIT, at Indian Institute of Technology, also known as Indian School of Mines, Dhanbad. Professor Prasad has been serving IIT Dhanbad for many years. He has completed his PhD in mathematics from BH in 2002. His research contributions span areas such as integral transform, pseudo-differential operator, wavelet analysis, and distribution theory. He is widely recognized for his scholarly contributions with a strong qualification and citation record, and has guided several research scholars in advanced areas of mathematical analysis and applied mathematics. Apart from research, Professor Prasad is also deeply involved in teaching and academic mentoring. contributing significantly to subjects such as functional analysis, real analysis, complex analysis, and data theory. We are honored to have such a accomplished researcher with us today. Now, I would like to call Dr. Ravindra Kumar, Assistant Professor, ECE Department, Government Engineering College, to kindly felicitate Dr. Rajesh. Sir, stage.
Thank you for coming.
Hey.
I want to connect reference from Korea. Okay. What is the
कहीं सारा कर दे पूरा लेक्चर स्टार्ट कर दीजिए तो वहीं से
signal by function which behavior is oscillating
दे देगा देखने यहाँ पे बोलिए
after some time it will return. And Wavelet transfer is the generalization of Fourier transform. Okay, so like Fourier transform, suppose f belonging to L1R, then f at omega is equal to 1 upon 2 pi minus infinity to infinity e to the power minus I omega x f of x dx. Okay, here kernel is e to the power minus I omega x. If we break this, this is the cos x minus I sin x. Okay, this is the cos x, this is the wave. Sin x also wave. And Wavelet transform W psi x dA minus infinity to infinity f of x and psi dA x dx, where psi dA x is equal to 1 upon under root mod A psi x minus d by a. Okay, so here this is the kernel of the Wavelet transform, and this is the e to the power minus ix is the kernel of Fourier transform. This is the cos x minus I sin x, that is the wave, and this is the wavelet. This is like after some time, right? So I want to connect from Fourier to Wavelet. Okay, This topic belongs to harmonic analysis. Why it is called harmonic? By Fourier series. Fx is equal to this. Okay? Suppose y is equal to this, and we know that the harmonic equation of simple harmonic motion. Y is equal to a sin omega t plus phi. So we can convert this as like harmonic equation. Okay? Due to this reason, this is the harmonic. So first, Joseph Fourier defined the series in trigonometric form. Any function can be defined. It is real periodic, that is this, and Fourier coefficient A0, A1, B1, as well as this. Okay. So here alpha plus 2s limit. If we put alpha is equal to 0, then interval 0 to 2l. If alpha is equal to minus l, then interval minus l to l. Similarly, and so on. If alpha is equal to 0, alpha is equal to pi. Similarly, this is 0 to 2 pi and minus pi. Complex form of Fourier series. We know that cos x is equal to field for ix plus field for minus ix upon 2, and sin x is equal to this. We put it in previous equation. Here we get this complex form. This is a complex form of Fourier series. Okay, here coefficient Cn and C minus n, where Cn is equal to An minus Ibn upon 2, and C minus n is that this one. C0, A0 by 2, Cn this, and C minus n this. What is Cn? This is the Cn bar, C minus n. Okay, and the complex of this, that is there. By putting the value of A0, An, Bn in equation second, that is here. Then Cn is equal to this, and similarly C minus n. This is the replacing n by minus n, that is this one. And Fourier series Fx is equal to in this R. Okay, and Cn this. Okay. Parseval's formula, we have Fx is equal to this, multiplying both sides, Fx, and integrating from 0 to L, and the coefficient 1 by L. So this is this part. Okay. So in this is the L2 0 to L. We can write this is not F square, and this is the this one, and using the coefficient formula, we get value of this is again C minus n, and Cn C minus n, that is this is the conjugate complex of Cn bar, C minus n is equal to Cn bar, that is mod Cn square. So now net square is equal to this. This is the important code. Similarly, this is the discrete sense. Fourier series, that is discrete. Similarly, Fourier integral. Okay, Fourier integral define this. This is the defined by some explanation. So only key part here I have given. Fx is equal to this. Okay, where a omega is equal to this one, as like Fourier series, in integral form. Okay. So fx is equal to, putting the value of a and b, we get this after simplification. We have c omega is equal I omega n. Okay, so this is the important point. You see, sometime Fourier transform defined this. Sometimes Fourier transform defined by this one. Accordingly, inverse Fourier transform we can convert. If Fourier transform defined this, so inverse Fourier transform 1 upon 2 pi and e to the power I omega x and f x omega d omega. Okay, and means it coefficient of Fourier transform and inverse Fourier transform multiplication of both should be 1 upon 2 pi. Okay, while we can adjust on here 1 upon 2 pi. Okay, suppose this is 1 upon under root 2 pi and 1 upon under root 2 pi is this. Okay, so this is the c omega 1 upon under root 2 pi. So this is the Fourier transform of c omega. C omega is the inverse Fourier transform of c. Okay, so c omega is equal to this. This is the function of c omega is known as the Fourier transform of f. Okay, well-known property. So we can take it. Linearity property, shifting property, scaling property. This is a well-known property. Dilation, convolution, F convolution G. What is the meaning of convolution? It is not multiplication. Then why we define it? F convolution. Suppose any transform has kernel. Okay, general definition, any transform f of omega is equal to kxy and f of x dx. Okay, so meaning of this is it is defined g t minus tau. This is the function of t and tau. Okay, so we can treat this as a kernel of this. So we can harm the several transforms with this property. Okay, Fourier transform of f convolution is this is Fourier transform of f into Fourier transform of k. And derivative property, Parseval identity, and Plancher's formula. This is a well-known property in mathematics. This is a very important function, Gaussian function. Okay, so Fourier transform of Gaussian function is Gaussian function. Okay, depending on A. So in terms of A, this one. Suppose if 1 upon k is equal to 1 upon under root 2, we get e power minus omega square upon 2. If Fourier transform, we take 1 upon under root 2 pi, then Fourier transform of Gaussian function is Gaussian function without 2. Okay? Here, question, does G belonging to L1R? F convolution G is equal to F. Where F belonging to L1R? To define the Fourier transform, we need F belonging to L1R. Okay? So, here F convolution G is equal to F. That where F belonging to L1R, this is the question one. I am. We know the property F, Fourier transform of F convolution G is equal to Fourier transform of F into Fourier transform of G. Okay? So, okay, so taking the Fourier transform of this equation. So F cat D cat is equal to F cat. So G cat omega is equal to what? So this contradicts the Riemann-Leibniz lemma. If what is the Riemann-Leibniz lemma? If omega tends to infinity, then F cat omega tends to 0. Okay? So Fourier transform minus infinity to infinity, and here G cat omega is equal to 1. This is a fixed, not 10 to 0. Okay? So this contradicts the Riemann-Leibniz lemma. Okay? So answer is it is not belonging to L1. We introduce the sequence Dn. Yes, that is sometimes we can take the example of Gaussian function. Okay. So Gn omega tends to 1. Here we have suppose sequence Gn. At omega is equal to 10 to 0, that is 1. Okay. So Dn integral minus infinity to infinity dn t dt is equal to 1. How to say? Dn is equal to n upon under root 2 pi square minus n square t square. This is the Gaussian function. Okay? Yes, I can read. So Gn cap omega is equal to then Gn cap 0 omega 0, that is integral Gn t dt. Okay, and Gn 0 1. This is a good example of the sequence GNT, Gaussian function. Gaussian function is this one, and G cap omega is already discussed. So, Dirac delta function. So, even though delta not belonging to L1R, so we define already defined Dirac delta function, where delta not belonging to L1R, because F convolution G delta is equal to F. which means that delta plays the role of the identity element in L1R. Clear? So F cap omega delta cap omega is equal to F cap omega. So F cap omega, that is delta cap omega, is equal to 1. So delta is equal to 1 upon 2 pi is for I omega t. So we transform of the delta t. And delta cap omega is equal to 1. So derive delta defined in terms of equivalent real function. Okay. So delta t is equal to, this is the one function. So noting point here also delta t defined by this 1 upon 2 pi integral minus infinity to infinity cos omega t dt by in for I omega t cos omega t plus I sin omega t. Okay. So and this is the given function, real and imaginary part, equating the real and imaginary part. So delta t is equal to this is imaginary part. Okay. This is the main definition or derivative. Delta t is equal to infinity if t is equal to 0, if t not equal to 0, that is 0. And integral minus infinity to infinity delta t dt. And this is sometimes defined delta t minus a. So if putting t minus a here, so t is equal to a. So delta t minus a equal to infinity, t is equal to a, and 0, t not equal to a. And by this integral minus infinity to infinity delta t minus a dt. Good example of this Persian function. Sometimes this is n tend to 0, this also we convert this in epsilon tend to 0, so we can write this equation. So clearly delta n t tend to infinity as n tend to infinity for t equal to 0, and delta n t tend to 0 as n tend to infinity for t not equal to 0. Okay, explanation. When t is equal to 0, so we take example this. Okay, so here t is equal to 0, limit n tend to infinity delta n t, and limit n tend to infinity n upon under root 2 pi, and as t is equal to 0, it is for 0 1. So and n tend to infinity is tend to 0. At t is equal to 0, this is tend to infinity. And t not equal to 0, this is the delta n t equal to 1 upon under root 2 pi, limit n tend to infinity n, so minus n square t square, this is infinity by infinity case. Okay, so differentiating numerator and denominator, so this is in denominator, so we have this one, and putting n tend to infinity, we get 0. Yeah, here is it. We applied L-Oscar rule.
पास कर रहे हैं उसने का लोग गलत कदम निकाल
So also start n equal to 1 to 3, this is an integral theta n dt or minus integrate is equal to 1. This is the explanation. Delta t, again tends to infinity, we find delta limit n tends to infinity, delta n t is delta t. So putting the value of delta n t
इनका तो वो भी ठीक
and
ये सिक्स दिया गया
n upon under root 2 pi for minus n square 3 square dt and by gamma function value of this is okay value of this under pi minus property. These are the properties of related transfer. Okay, minus delta t minus a is equal to f of a, which is the eigen function. So we can write your answer. And it is equal to 0, that is we have this integral f t delta t dt f of 0. Delta x is equal to 1 upon mod a delta x and minus delta minus t equal to delta t x, which is the derivative. Proof. Let delta epsilon greater than 0, epsilon greater than 0 means epsilon greater than 0. So value of delta epsilon t minus a is equal to this one in terms of the Gaussian function. Okay. We can write this is t minus a whole square, so this is delta epsilon minus a minus t, we can write it also. Yes? Either you write a minus t, no problem. This is square. So that is a minus t, so you can write a minus t. So which satisfies this condition, this one. Epsilon tends to 0, this representation is delta t minus a. Then integral f t delta epsilon t minus a dt is equal to value of this from here. Putting t minus a upon epsilon is equal to s and t is equal to a plus epsilon s and dt is equal to epsilon ds. Then we have this equation and epsilon tends to 0. Then f of a plus epsilon s is equal to f of a. Okay. So therefore delta t f of epsilon delta t minus a is equal to f of f1 under 2 pi and f1 minus x squared. Value of this is root pi. Root pi cancel away. When a is equal to 0, that is integral f t delta t, this is equal to f of. Delta ax. Second property, delta ax is equal to 1 upon mod a delta x. Okay. So putting a, we have the formula delta x is equal to already discussed, delta x is equal to 1 upon 2 pi for I omega x. Okay. Earlier. Fine. So delta ax is equal to this one, putting ax is equal to t and x is equal to t by a, and this we get 1 upon a 1 upon 2 pi integral e to the minus I omega t So this is 1 upon A delta T. Okay. Here A belonging to R. So in combined way, this is part A. Okay. So if we third delta minus x is equal to delta x, that is given. So putting A is equal to minus 1. Okay, in this. We get delta minus x is equal to delta x. Derivative property. This is integral minus infinity to infinity ft delta dash t dt is equal to limit a tends to 0 integral minus a to a ft delta dash t dt. So this is integration by parts. So this is first function integration of second, this minus a to a, and differentiation of first and integration of second and integration. Okay, so f of a delta a and minus f of minus a delta minus a minus delta x 0. Okay, so delta a is equal to 0 if delta t is equal to 0 if t not equal to 0. Okay, so here a not equal to 0, that is 0. Is also 0. And we have third part minus delta here. Repeating in this way, we get our energy differential. Okay. Stationary function, generally Fourier transform applied for the stationary function and Fourier transform non-stationary. Okay, so this is there is no amplitude. That is the stationary here, and after this is the shifting means only shift the position. And here the amplitude. So as a Weber transform, this is not stationary. Sometimes this amplitude varies to non-stationary. Weber transform in Weber transform we generally use non-stationary. Okay. So Fourier transform by stationary function. What is the drawback of Fourier transform? There is no time location. Okay. Weber transform defines this, and Fourier transform defines this. Here two variables, B and A. What is A? This is the frequency. Okay, and this is the time location T. This is equal to T, the time. This is B. This is the time location T. Okay. So here we can find, but time location not. For Fourier transform, at the time location we can find. So before of Weber transform, in stationary function, this is Fourier transform, this is drawback. Then the word transform thought, what will be the for the stationary function and for the time location. Okay, so after Fourier transform, Gabor defined it, Gabor transform as time location. Okay, using the Gaussian. This is G alpha B, just like this. B A. Here, this is the coefficient. This is the kernel of the Fourier transform, and This is the Gaussian function at TDT. Gaussian function, suppose 1, that is the Fourier transform. So, here, we are finding Gaussian function. So, in this transform, frequency and time and location B also. But this is the fluctuation at the low frequency and the high frequency. Okay, so not for all times. Situated by the means it exists. Okay, I will discuss in a favorite transform. So these are the property of Gabor transform. Gabor transform localized with Fourier transform. Okay, so this is a simple calculation. The integral minus infinity to infinity Gabor transform differentiating with integrating with respect to t is equal to Fourier transform. So this is a simple calculation. My motive is to there was a lecture on Western transform. Okay, so this is a simple. So value of this one is 1 already defined. This is the whole transform defined by this is a function like kernel. This is a kernel of the. What is the kernel? Kernel of the transform. Fourier transform kernel is this one. In Fourier Wavelet transform kernel is Wavelet function. In Gabor transform kernel is this one. E for minus I omega t and T of 30 minus. All terms except Ft is the kernel. Yeah. This is and the part this is behind of it. That's notation. This is the answer some property of this. Okay. So Fourier transform of the Gabor function is this one, and Gabor transform. Gabor transform defined by this one is equal to A. What is the Gabor transform? Gabor transform, just like you have seen in this equation. E for minus I omega t, d alpha t minus d, and E of r t. Fourier transform here. Also defined. Gabor transform was this one. Here, this is the kernel of the inverse Fourier transform. Okay, and this is the exactly Gaussian function. Okay, in alpha there and here on 1 to alpha. Okay, except this part. So we can define inverse Fourier transform. Gabor transform, also known as the star-time Fourier transform or window transform. Window Fourier transform. Star-time Fourier. We got the property there. Some property. Motivation why wavelets? Okay, wavelets are a special kind of function which exhibits oscillatory behavior or short period of time and then direction. Wavelet analysis means analyzing a signal with short duration time energy function. This analysis transforms the signal into more useful representation. This transform of the signal is called wavelet transform. Unlike the Fourier transform, we have variety of the wavelets. That's here Fourier transform on the fixed kernel, and wavelet transform we have this option, so many wavelets. Okay, so that are used in signal analysis, such as Haar wavelet, Morlet wavelet, Mexican Haar wavelet, Turkish wavelet, Anglais wavelet, etc. We manipulate wavelets in two ways. First, in translation, we extend the central position of the wavelet along with the time axis, and secondly, ellipse. This is B is the shifting translation, and A is direction. Okay. This is defined in two ways: continuous and discrete. Okay. So AB transformation process is done in a smooth and continuous fashion. Then the transformation is called the continuous, and it can change in discrete state. The transformation is called the discrete. This is a signal. Okay, this is a signal, and here this is the wavelet transforming signal. Changing from yes, this is the wavelet. Okay, so first, Morlet modifies the Gabor function. Gabor function is this. So oscillate rapidly, omega tends to infinity, leading to numerical instability in the computing coefficient. And at low frequency, the oscillation becomes very slow. These difficulties led to the problem to finding the suitable reconstruction function. In order to resolve this difficulty, Morlet first made an attempt to use analytic signal. This one, as they can answer. So he thought, what is the Fourier transform, and introduce first wavelet size defined third the wavelet function. First, if Fourier transform, if we have the such type of any function, Fourier transform, psi hat this one is equal to this omega tend to greater than 0, and then this wavelet corresponds to analytic signal related to the second derivative of the Gaussian function. This one and got 1 minus t square e to the power minus t square by 2. This is. Which is the inverse Fourier transform of the, and then inverse Fourier transform of psi hat omega, yes, with you, and this is psi t equal to 1 0 is defined. Thus, the modulated wavelet turn out the modulated Gaussian function e to the power minus t square upon 2 e to the power I omega 0. Then psi t. Suppose actually if we take only this part, e to the power minus t square by 2 e to the power I omega 0 t. Okay? If we take this part of this function, actually main function is this. But here we have seen function is this one. If we take this function, so admissibility condition of wavelet transform not given. Okay. So if we take omega 0 greater than 5, then no change, more change this function and satisfies it in admissibility condition. Okay, so we can take without hesitation, we can this. And Fourier transform of this is this one. Usually omega 0 greater than or equal to 5, the correction term is teeny, very small, and is often ignored. So we have this one and psi t is equal to e to the power minus t square omega 0. This satisfies the condition psi hat 0 is equal to 0. I will discuss again ahead. T psi is equal to minus infinity to infinity mass psi hat omega square upon okay, here psi hat omega here okay, so psi hat omega tend to 0. Okay, this is integral minus infinity to infinity psi t dt. Okay, and psi t dt psi hat 0 0. Okay, so if psi hat omega 0, then this is psi hat 0 is equal to minus infinity to infinity psi t dt is equal to 0. Means suppose R wavelet or any wavelet, this is one part and this is the total 0. Okay, so total sum 0. So psi, but if we take without this admissibility condition not given. And one more question arises here. Why we take this? admissibility condition, this one. Why not Q, O, etc.? This is have you seen earlier? I will discuss that. Okay, so I calculate the 0, that is the basis of estimate. Based on translation, scaling, and scaling single function size called the mother reference. This is the mother. Starting from this. So we can then this is a size baby. This is the baby reference. Data. Okay, A is scaling, B is the translation, size B is the mother wavelet, and the function size A is the called the data wavelet. And the scaling function is father wavelet. Okay, so here we have two parameters, A and B. Okay, so suppose here B0, that is size T by A. A is real. Okay, so this is type of size T by A or size A. Okay, so this is the nature of this wavelet, shrinking or expanding. Means as is depending on the A. And here wavelet, and what is the role of B? Shifting the position from first, this is this one, and shift sometime after B, this and this. So B shifting the position. Okay. Proposition. If psi belonging to L2R. Okay. So L2R, then psi BAT also belonging to L2R. Right? So our L2R, we check the norm of L2 psi BAT. This is defined this. And putting the value of psi BAT, this one, and putting the PA minus B is equal to X, then this one, and this is norm of square. L2 norm of psi BAT is equal to L2 norm of this. Okay. Yeah. Next, Fourier transform of psi B effect. Fourier transform of psi B effect using the definition of Fourier transform is for minus I omega t psi B a t, and putting the value of t minus b by a equal to s and t equal to ax plus b. Okay, t is equal to ax, you can remove the mod, no problem. Or the mod. So this is this one. And after simplifying, we have the result. Here, psi cap omega is equal to this. Okay. From the group theoretic point of view, the wavelet psi B can be seen the result as UAB. Okay, this is a affine group. Group properties, composition of the UAB. UAB means size AB, size BA, size BA. Okay, so this one and this is the identity property and this is the equals property. Here this group UAB size UCD size is equal to, suppose this is as a function. Okay, applying first UAB. So this is d minus d by a type. So this function, and again we apply this. So x minus d by a minus d, here d and c, and then we have this one, and as per the definition we can write. And identity u10 is equal to here p0, this one, that is this is the silent identity. And inverse, we have the result this one, and UAB inverse is equal to this, and this is the identity. UAB inverse is equal to U of 1 upon A, B upon A. By this one, and like this, that is it. Okay, already discussed it. Okay. This is a compact supported wavelet, that is a hard wavelet. Okay, this is the support is 0 to 1. So you know support where function is non-zero. Okay, that is support. Here 0 to 1, 0 to 1, function is non-zero. This is type of. In localization property, you can check the function is wavelet or not. Integral psi t dt tend to 0. Okay, in frequency domain, you can check by additivity condition. Here, I'll check psi x is equal to 0. And this is a frequency domain R. C psi is equal to this one. Okay, already discussed psi at 0 is equal to 0. Okay, that is psi t is equal to 0. And one property is this, and another property mod psi t square dt is equal to 1. Okay, so by definition, the balancing moment. Balancing moment, the wavelet has n balancing moment if satisfies the condition this one. Tk integral minus infinity to infinity psi t for k psi t dt is equal to 0. K is equal to 0, 1, 2, and 1 and minus 1. Equivalently, this is this one. Meaning, if I have n vanishing moment, then it is orthogonal to all polynomial of degree less than n. Okay. Modeled wavelet has exactly one balancing moment. One balancing moment means this is the condition, this one. Only this condition, not satisfied this condition. Second balancing moment, n is equal to 2. Means 0 and 1. First, this one, and second is for a equal to 1. This is property. Now, wavelet is orthogonal to constant linear function. Why balancing moment? Suppose here ft psi abc. Okay, if suppose you like this, so putting this one, so it can say by the Fourier transform, is equal to 0. So this is the explanation of the balancing moment. Psi cap omega is equal to this one, psi t per minus omega t. So at last we have this one result, and expanding in Taylor series are okay. First part that is 1 and psi cap k is equal to this. At particular omega is equal to 0, then psi cap k 0 is equal to this one, and t k psi k dt is equal to 0. Suppose the wavelet has n balancing moment, then this one is equal to this thing equal to 0. At k is equal to this one. If n is equal to 2, it means one condition this one is 0 and three balancing moment, then this condition t and another t square psi t is equal to 0. For example, Haar wavelet. Haar wavelet define this in the interval 0 to half, 1, and half to 1, minus 1, as well as 0. So psi t, integral minus infinity to psi t dt, 0 to half to 1. Solving this one, this is half minus half is equal to 0. Okay? And we can check on the second t psi t dt, this one, and solving this one, this one, not equal to 0. Okay? So it has only one balancing moment. Mexican height wavelet. Here psi t 1 minus t square is 1 minus t square by 2. This is the Mexican height wavelet. And value of the integral minus infinity to infinity psi t dt is equal to this, solving this is 0. Again t psi t dt, solving this is 0. Since the integral is an odd function, and further this is t square psi t. Further this one, this is not equal to 0. So it has only Haar wavelet, this wavelet is very well applied the time domain, but it is not a continuous. Here, not one. Fourier transform of higher select. Okay, I want to check in frequency domain. Okay, psi cat omega this one, psi is already defined hazard 0 to half and half to 1. Okay, so this is divided in several parts minus infinity to 0, 0 to half, half to 1, 1 to infinity. Okay, minus infinity to 0, that is 0, and 1 to infinity also 0, and 0 to half psi is equal to we are defined 1 and half to 1 minus 1. Okay, so starting this one, we have this. And simplifying this, that is 2 I sin omega by 4, is 1 minus I omega by 4. So psi cap omega is, and I apply this one here. So we can check by the admissibility condition. Admissibility condition is by frequency domain. Okay. So here psi cap value of the psi cap putting this and this one. Okay. So this is mark. Okay. Event function. This is also event function. This is if psi is reference and phi is bounded integrable function, then convolution function is a reference. Suppose phi belonging to L1R, okay, yes, we get phi is bounded integrable function. Okay, that is this one. And phi cap infinity null, these are equal to null phi 1. Okay, so you can take here, this is suppose taking the modulus value of the Fourier transform, and this is less or equal to this, which is 1 and mod f. Okay, so supremum of this is the infinity null and mod f is the null. So less or equal to okay. So now convolution, psi convolution phi defines this by definition of the convolution. So first we have to check the L2 now. If function here these properties define if psi belonging to L2R. Why L2R? Why not LTR? LT not? Actually, W psi f defined by this formula. Okay, what is this? This is bar. Okay, we can write this is the inner product of psi VA. Okay, using the Parseval identity. Using the Parseval identity, this is 1 upon 2 pi phi cap psi cap. Okay, so we can apply this formula when function belonging to L2. Okay, so due to this reason, to actually continuous Weber transform defined is phi belonging to L2R due to that reason. So first we check the function is L2 belonging to L2 null or not. L2 or not. Okay. So this is the if this less than infinity, that is the L2 null. So this is high convolution phi. By definition, we can put here. Okay. Then this function can be divided in two parts, I half. Okay, and we take one part and this is one function. They are like one function, this is, and using Holder's inverse, Cauchy-Schwarz inverse. Okay, Cauchy-Schwarz inverse as a Holder's inverse, T equal to 2, that is Cauchy-Schwarz. Okay, so you can write Holder's. Okay, first part, this is square of this, or 1 by 2, this is here square, so only square. This and this. Phi is integrable function. Okay, already given in theorem. Okay, so again, this one, here, double integral, okay, so 1x in u, here x, so one part we can be integrated with respect to x and another part is u. Okay, so we have this is again putting the value of x minus u equal to n. Then this is the one part integrating with respect to u, that is x square, and this is bounded, already given, and this is psi square root. Okay, this is an graph, psi line equal to already. So total part is 100. Then phi belonging to L. Now we can check, otherwise you cannot check. First we have to check function is L2 or not. Moreover, Fourier transform of psi convolution phi. This is the property of additivity condition. Here condition this one. So Fourier transform of the phi convolution psi. Already defined in Fourier case, Fourier transform of the phi convolution psi is the Fourier transform of phi is Fourier transform of psi. Put it this. Here, so we can write this is psi square upon omega and phi square omega square. Okay. So taking the supremum value of this I cap omega, okay, in omega. So we can take the outside integral and we have this one, and this is the infinity condition of it. Psi and the value, this is supremum of already defined here, norm of high cap in infinity, these are equal to norm of high. So this is also finite, this is also finite. So it can be phi there and this will be continuous. Okay, so phi convolution phi is now we will let transform. Okay, so if the transform process is done in a smooth and continuous fashion, that is, then transformation is done continuous. And if position, the scalar position change in the speed system, that is. Any integral transform is an operator T on space of the function over space x. This is the general definition of the integral transform, where Kxy is known as the kernel. If kernel Kxy is equal to minus Ixy, that is Fourier transform. Okay. Can you compare the Fourier transform with Weber transform? Here, Weber transform behind this one, okay, and psi BA x minus B, okay. If position D 0, then this is psi by A. So psi by A 1 upon under root A psi by psi x by A if defined e to the power x, suppose. Okay, B0 and this one. So we can write here high alpha x is equal to high alpha x equal minus high alpha x. Here only dilation na. Here dilation only. In Fourier transform IXY, y dilated with x. Okay, so we can write this is the high alpha. There psi alpha x. This is we can write psi alpha x. Where psi alpha b, here only psi alpha, not location. Okay, so here Fourier transform this one, and here define fx psi b, where a0, and fixed here is secondary. Okay, so it means this is the Weber transform is the generalization of the Fourier transform. Okay, so Fourier transform is defined this. Yes, let me present to us. Some properties of the continuous Fourier transform. Here psi AB. Here B translated, shifting the property, and A dilated. It means T is a notation of translation, D is a notation of dilation. D B D A. Okay. And Fourier transform using this property, then we have the modulation, dilation is 1 by 3, where translation is defined here for P minus A, dilation 1 upon 3, and modulation. So sometimes you see the dilation function. Dilation function sometimes we defined DAF T is equal to 1 upon under root mod A F of A. We can ignore 1 upon modulus A. Can we ignore? Yes. Without this, you can define our result multiplication. Why is this? In orthogonal property, you have defined in this field test. Okay, I will discuss again later. Okay, so why we need 1 upon mod. Okay. Here, Fourier transform, continuous Fourier transform defines this, and putting the value of psi cat dA. Psi cat dA already defined its for A and some exponential form and a cat. Okay. So that is the Fourier transform of wavelet transform is defined this. Why? Proof. W psi f dA is equal to f psi inner product of f psi. This one. And inner product behind this integral form psi dA cat omega. Value already discussed in Fourier beginning. This one, okay, and putting the then W psi f dA is equal to here it is for I omega b and this part. Okay, so this what is this? This is the kernel of inverse Fourier transform. Okay, so we can write inverse Fourier transform of this. Okay, so taking the Fourier transform on both sides, Fourier transform defines the symmetry property. So that this is Fourier transform of this is equal to. Okay. Basic properties of wavelet transform. The linearity property, shifting property, scaling property, symmetry, parity, antilinearity, and suppose here translation in psi, then we have this schedule. If dilation in psi, that is in first, second, third, here dilation in function, yeah. Okay, and translation in function, and last two properties, translation dilation in psi. Okay, then we have proof. And one more, if you have homogeneous function, then W psi f lambda A lambda B. Linearity property, W psi alpha f plus beta g is equal to this one. Why? Because W. Okay, after T.
Thank you, sir, for the wonderful lecture. So we will be in the next. T is outside. Have a nice day.
हम भी लग जाएंगे। कहाँ से? कौन खिलाया? कौन खिलाया? वहाँ के घर पर बात है, पहले खाते चले आए। समोसा है जाओ ना, दो समोसा है। ये बोला मैं ऐसे खाने का मन छोड़ दे। पहले पानी को